is different. So this is a special occasion where we are gathered to commemorate the birth centenary and celebrate the life work and legacy of one of the most brilliant minds in the history of physics, P.W. Anderson, whose contributions have reshaped our understanding of condensed matter physics and have left an indelible mark on science as a whole. P.W. Anderson, sorry, 1 minute. I have started the recording. P.W. Anderson, or Phil, as he was affectionately known, was a visionary whose insights into disorder and complexity in physical systems were nothing short of revolutionary. From his early work on magnetism and theory of superconductivity to his more recent contributions to the theory of complex systems and the concept of Anderson localization, his work continues to influence physicists and researchers around the globe. On behalf of IAPT Regional Council RC-23 Himachal Pradesh, I would like to welcome the President of IAPT, Professor P.K. Ahluwalia, Secretary of IAPT, Ma'am Rekha Ghorpade. In today's program, we have two special personalities who are not only active in teaching and mentoring young physicists in India, but are part of broader Indian physics community that has been influenced by Anderson's legacy. We will hear first from Professor T.V. Ramakrishnan on the topic Anderson's stance in physics, and then from Professor G. Bhaskaran on the topic Secret of Anderson's success. So I welcome you, Professor T.V. Ramakrishnan and Professor G. Bhaskaran from IAPT Regional Council RC-23. I also extend a warm welcome to Professor P.C. Deshmukh, who will chair today's session. I want to welcome all the dignitaries from India and abroad and all the participants for joining us today. I hope that this celebration will not only honor his memory, but also inspire us to continue the work Anderson so passionately dedicated his life to. Welcome and thank you once again. So before we start the session, I would like to give a brief introduction of our today's speakers and the chairperson of today's session. Our first speaker for today's session will be Professor T.V. Ramakrishnan. And those who have joined us today only, I would like to give brief introduction of Professor T.V. Ramakrishnan. He is a distinguished and internationally recognized Indian physicist whose groundbreaking contributions to condensed matter physics have shaped the course of modern theoretical research. With an illustrious career spanning over 6 decades, he holds a prominent position as a distinguished associate at the Center for Condensed Matter Theory, Indian Institute of Science, Bangalore, and has served as a professor and researcher at several prestigious institutes worldwide. His academic journey begins from Banaras Hindu University, followed by from Columbia University, New York. Professor Ramakrishnan's scientific work is renowned for its profound impact on the study of disordered systems, quantum physics of many electron systems, and theoretical biology. Throughout his career, Professor Ramakrishnan has held numerous prestigious positions, including visiting professorships at Princeton University and Cambridge University, and has received several high-profile honors such as Shanti Swarup Bhatnagar Award, the Triste Science Prize, and the Padma Shri from the Government of India. A fellow of many leading academies, including the Royal Society and the Indian Academy of Sciences, he has been recognized as one of the India's foremost scientists. In addition to his research, Professor Ramakrishnan is deeply committed to science education and communication. He has made significant contributions to textbooks and popular science articles, bridging the gap between complex scientific concepts and the broader public. His passion for teaching is reflected in his role as a key contributor to NCERT physics textbook used by millions of students across India. So we welcome you, sir, in the second day of this webinar. Let me introduce our second speaker also, Professor G. Bhaskaran. He's a distinguished theoretical physicist, renowned for his broad-ranging expertise in quantum matters, with a keen focus on the exploration of room temperature superconductivity, novel quantum phases, and qubits at ambient condition. His research continues to push the frontiers of our understanding in these forward-looking fields. Deeply inspired by the wonders of nature, biology, and neuroscience, Dr. Bhaskaran's intellectual curiosity extends far beyond traditional boundaries, seeking connection between the physical sciences and living world. Professor Bhaskaran's academic journey began in the vibrant city of Madurai, where he completed his school education, followed by MSc in physics at American College, before earning his PhD in theoretical physics from the prestigious Indian Institute of Science, Bangalore. In 1987, he joined the Institute of Mathematical Sciences in Chennai. He is a distinguished professor at IIT Madras and a distinguished visiting researcher at Premier Institute for Theoretical Physics in Waterloo, Canada. A fellow of Indian Academy of Sciences, the Indian National Science Academy, and the World Academy of Sciences, Dr. Bhaskar's work has earned him numerous awards, including ICTP Award, the Shanti Swarup Bhatnagar Award, the Distinguished Alumni Award of IISc, and G.N. Ramachandran Award for Theoretical Physics from Sastra University. In addition to his scientific accomplishments, Professor Bhaskaran is passionate about sharing his love for science with the broader public, writing extensively on popular science in Tamil and making complex ideas accessible to all. So we welcome you, sir, in the second day of this webinar. So let me introduce to you Professor P.C. Deshmukh also, who will chair today's session. Before I hand over the mic to Professor P.C. Deshmukh for further proceedings, Professor Deshmukh is the convener and mentor of Center for Atomic, Molecular and Optical Sciences and Technologies, CAMOS, which is joint initiative of IIT Tirupati and ISER Tirupati. Currently, he is RP Chair Professor at the School of Computer Science and Engineering, RV University, Bengaluru, and also the Chief Technology Advisor to Vivekanand Institute of Professional Studies, New Delhi. Dr. Deshmukh has authored quantum mechanics, formulation methodologies and applications, and also foundations of classical mechanics, both published by Cambridge University Press. About 200 of his video lectures covering 4 full-fledged courses are available on the internet. These have been published by the NPTEL and Swayamprabha. He has also taught undergraduate and graduate courses and guided graduate research at IIT Madras for over 3 decades, and also at IIT Mandi, Georgia State University, Atlanta, and at IIT Tirupati and the ISER Tirupati. Professor Deshmukh's research group is one of the leading contributors to relativistic many-body studies of attosecond dynamics in atomic photoionization. So welcome, Professor Deshmukh, to second day of this webinar, and I hand over the mic to you for further proceedings.
Thank you. Thank you very much, Dr. Sapna Sharma. We had a great start for this webinar series yesterday. There were 2 brilliant talks, Professor Aluwalia's talk, followed by Professor Ramakrishnan's yesterday. And it is as exciting to listen to Professor Ramakrishnan and to Professor Bhaskaran as it is to celebrate the legacy of Professor Phil Anderson. He is not just decorated by the Nobel Prize, but he's one of those like Professor Van Vleck and Neville Mott, who decorate the prize itself. So we have 2 brilliant talks this evening. And let me invite Professor Ramakrishnan to speak on Anderson's stance in physics. Professor Ramakrishnan, welcome.
Yes, please. Thank you very much. I'm very grateful to Professor Ahluwalia and to Professor Deshmukh for chairing this session. I would like to share some gleanings of what I could gather about Anderson's stance in physics. My own guess is that this stance as a scientist flowed from his being an acute observer and creative interpreter of nature. So in that sense, he was a great natural scientist somewhat like our own great C.V. Raman, who was a true natural scientist, one of the few last great natural scientists. Anderson's being a natural scientist, it is being an observer of nature, being inspired by natural phenomena and experiments. This showed itself in a number of his contributions to physics, as I will try to describe. I do not know what was the origin of his this particular stance as an acute observer and creative interpreter of nature, but perhaps it can be connected with his early environment. He grew up in the Midwest of the United States, in Urbana-Champaign, where his father was a professor of plant pathology at the University of Illinois. He describes his childhood and boyhood as an idyllic period which has gone by, so definitely in the United States and perhaps elsewhere in the world. It was an open, healthy culture, close to nature, very scientific. This has been actually remarked on by many people, but I will not expatiate on this more. I would rather concentrate on his way of doing physics. And this is a slide, much of which I showed yesterday. And it actually summarizes his way of doing physics and his beliefs. He believed that many of the facts which nature confronts us with are so implausible that just demonstration of a reasonable mechanism leaves no doubt of the explanation. And he also believed that a simplified model is very crucial for this purpose, because it throws more light on the real workings of nature than any number of ab initio calculations of individual situations in which this phenomenon occurs. This skepticism was expressed quite explicitly over his career. And in his Nobel lecture, he says that it can be a disadvantage rather than an advantage to be able to compute very accurately, because the perfect computation simply reproduces nature, does not explain her. So that with that, I will start on a few basic philosophical underpinnings or motivations for his approach to physics. This is just to enable us to think more coherently about what he did. And it is not to say that he had a very clear, well-defined, well-articulated, detailed philosophical position, as a consequence of which many of the contributions he made in physics came out. That's not so, and that doesn't happen to almost any physicist. However, he did have many strongly held beliefs. One of them is that physics is a natural science, namely, which this doesn't need much. I mean, this is obvious because, after all, modern science is natural science. And he, in particular, was very close to the views expressed by Francis Bacon, who is considered one of the founders of modern science, and who believed that experimentation, which includes, of course, observation, which also includes controlled experimentation, this is essential to discovering natural truths about nature. So I give here I mention here a quote, phrase from a sentence from Francis Bacon's Novum Organum, in which Bacon's ideas about what science should be are put together. Bacon said that once the particulars have been gathered together, the interpretation proceeds by sorting them into a formal arrangement so that they are presented to understanding. This implies the following thing, that you start with phenomena which you observe or which you notice by experimentation. Then out of these phenomena, you form some hypotheses and some models for describing these phenomena. Then these are refined into theories. And once you have a theory which is generally expressed in a mathematical language, then you make some predictions. And these predictions are new phenomena. I mean, they give rise, they sort of motivate you to look at to make experiments which check whether these phenomena occur or not. And if they occur, well, then you find that some unexpected thing also occurs. Then you make a slightly more detailed hypothesis, and then a slightly more detailed theory. And so there is a continuous chain of this kind. But the fundamental in modern science is the first link, which is the phenomena. This is the position which Anderson held very strongly. The question then is, what kind of phenomena? Here Anderson made a very significant assertion and a departure, which it is this, that in many areas of science, in nature, phenomena and properties emerge. They emerge out of the constituents of this particular piece of matter or a particular organism or so on. And Anderson felt that to recognize this emergence is especially necessary in physics. This is important for us physicists because reductionism has worked so well. That is, the idea that the essence of the phenomenon is resides in simplifying the substrate of the phenomenon, where the phenomenon lives, into something simple, which captures somehow the essence of the phenomenon, and then developing the consequences. Now, this actually works extremely well. It has worked well over so many centuries, and it is very deeply embedded in our head that this is what physics is. We think that this is the only way. But this way, if taken quite far, leads to a mechanistic view of the universe. This I have tried to show in a cartoon of a duck. This duck is shown here as a machine. I mean, that is, it is shown, it tries to assert that no, the digestion process of a duck is purely mechanical. I mean, it ingests something, then there is a pipe, and then through that pipe, something goes into a place where lots of things are churned and digested, and something is produced. Now, this we now know is not quite so literally true. But this kind of reductionist, mechanistic view is extremely common and extremely powerful. For example, take the solar system. I mean, solar system consists of the sun, the planets, and the planets have moons. So it's really extremely complicated. Now, we don't, and then of course there are meteorites, etc., etc., and sort of occasional visitors. We do not consider all of them at once. We try to simplify matters. We simplify matters by saying that, oh, well, we can think of the sun as the center of the solar system. It's very heavy. It doesn't move. Maybe it is of an infinitely large mass. And then the planets are, let us like points going around the sun, and they go around the sun in elliptical orbits. Then we introduce more and more elements of reality, like moons for these planets, perturbation of other planets on a particular planet, perturbation of the moon on the planet in the form of tides and so on. And we are able to build a very successful picture. So we feel that this is the only way to do physics. This is also seen at the other end of scale. I mean, the solar system is a very large scale object. Our study of matter, basically going inwards from molecules to atoms to nuclei to subnuclear particles, finally ends up in the belief that if you have a knowledge of elementary quantum fields and basic forces, it is sufficient, it is necessary as well as sufficient to understand all natural phenomena. Now, emergence, I don't think it has any quarrel with the belief that it is necessary, but I think it questions whether it is sufficient. And let me talk a little bit about that. This is the reason the idea of emergence questions the sufficiency of a reductionist view is that we know very well that the whole of a system is more than the sum of its parts. For example, we are sort of we are a bag of chemicals. 80% or more is water, and so on and so forth. And there are so many chemicals in small amounts, large amounts, and so on. So many complicated molecules, bacteria, viruses, all of these things are living inside us. All of these things are coexisting. But to describe a human being as just a bag of chemicals is not quite complete. And that is where emergence makes a difference. So in order to stress this point, I would like to quote from a very famous article of his, which was referred to yesterday, which is called more is different, which problem makes there is that the ability to reduce everything to simple fundamental laws does not imply that we can start from these laws and reconstruct the universe. Instead, at each level of complexity, entirely new properties emerge. The understanding of new behaviors requires research, which I think is as basic as any other. So this was a kind of, at that time, perhaps it was considered a very challenging statement. But now there are just so many practitioners of this, so many ways in which this is confirmed to be true, that it is no longer an outlying assertion. He also said that the constructionist hypothesis, that is the idea that you can construct the whole universe, all reality, all physical phenomena, all physical facts, all systems, this is a belief. This hypothesis breaks down, he felt, under at least two conditions. One is the scale of the system. If the system is very large, very big, then it is difficult to construct. Only knowing, construct in the sense that construct it as you see it, with all the properties which you see it, it is impossible to construct. And also, if the system is very complex, then it is not possible to simply knowing the basic laws and constituents to construct the actual system. So one may believe that, okay, this is fine, but this leaves the door open to almost any possibility which may occur. And yes, it is indeed true that there is a huge variety in emergence. That is, if you put things together, very different kinds of things can happen. I mean, this is talked about in somewhat simplistic terms by saying that, look, you have maybe just 92 elements, and you put them together in different ways, and you get all kinds of compounds, all kinds of materials with very different properties. You get magnets, superconductors, solids, liquids, ferroelectrics, and so on. The very fact that there is a huge variety in emergence means that you really have to look for, if you want to really explain in any serious way a particular kind of emergence, you have to search for an appropriate specific mechanism which leads to the emergence of that property. The existence of emergence also is an antidote to a belief which was very common in the 80s. It is not so vigorously discussed these days. It was the belief that the end of science is near. This belief is that well, I mean, almost all the major things which had to be discovered in science have been discovered, and all that remains is just some details. However, if there is emergence, then continually new behavior, continually new properties will emerge out of new kinds of systems you make, new kinds of systems materials you find, and so on. And therefore, science will not end. So it's a very, I would say, a very optimistic view of science. It is a very strong counter to the belief that science will end. The other thing which Anderson emphasized in his work was was what is the nature of explanation, and he believed that explanation should be quite simple. That is, you should be able to explain some very obvious, strange behavior out of this rather simple ingredients which you have. So here I quote from Einstein, who said that it can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as clear as possible without having to surrender the adequate representation of a single datum of experience. Anderson, in his book, More and Different, which is this sort of last book, which is associated, which he wrote in an essay, he asked the following question. The origin of magnetism has been puzzling people for a very long time. And Pierre Weiss in 1905 said that, if there are atoms and so on, or even if they are not, there is something called a molecular field, molecular magnetic field, which exists in these materials like iron, cobalt, and nickel. And the existence of this molecular field is the cause of their magnetism. Now, this is an explanation, but this is a very inadequate explanation because it replaces one mystery, which is magnetism, with another mystery, which is molecular fields. On the other hand, Heisenberg, in the very early years of quantum mechanics, he showed that if two magnetic moments or spins are they interact with each other, then from quantum mechanics, you find that their wave function has to be such that there is an effective interaction between the magnetic moments. Now, if you have a collection of such magnetic moments, then it turns out that under certain conditions, spontaneously a molecular field, a non-zero molecular field will develop in some systems, and they are the ones which we know as ferromagnets. So Anderson felt that this kind of explanation is the real explanation because it goes to the basics, proposes an extremely simple model, and on the basis of that simple model, shows the inevitability of another very definite, mysterious phenomenon. Okay, so what I will do in the half an hour or so which I have is to discuss in some detail some examples from Anderson's work which illustrate his stance. You see, talking about the stance in the beginning is not a very good thing, but talking about all his work is also not a good thing because it is not physically possible in an hour. So I will just pick just a very few contributions by Anderson and show how they illustrate his beliefs. Okay, so the first thing I will take up is what is called Anderson localization. This arose from the following situation. He considered a very simple model for an electron moving in a disordered medium. Now, if an electron moves in an ordered medium, it just moves ballistically. It just like a stone, stone thrown from the top, it just falls. Similarly, an electron just moves in a straight line with a constant velocity. However, if the medium in which it moves is disordered, it's not ordered, then the electron doesn't move in a straight line. It diffuses. That is, it sort of moves in what may be called a random walk manner. It moves in a straight line for some time, then moves gets scattered, then moves in another direction for some time, and so on. So this is sort of well known for more than 100 years and believed to be true. And there is a lot of evidence that this is true. So an electron moving in a disordered medium will just diffuse or move randomly. then it seems natural that, okay, if you increase disorder, if you have more disorder, it will diffuse more slowly. It will, it will be more sluggish. Then what Anderson found was that if you have even more disorder, then it's not that it diffuses even more slowly, but it suddenly stops diffusing. It localizes. So it's a very strange thing that just plain disorder can stop an electron, in this case, from moving. This has enormous consequences. One of them, in the case of the electrons, is that a metal, which is what you have when electrons diffuse in a disordered medium from one end of the metal, for example, a wire, one end of the wire to the other, well, current is flowing. But if the electron stops diffusing, then no current flows. So it becomes an insulator. So a metal can turn an insulator if you increase disorder. Now, this kind of thing can happen for any wave. That is the implication of Anderson's work, because electron in his model for electron moving in a disordered medium is considered a quantum wave, quantum particle, and so it's a wave. For example, it has been shown that this can happen to light waves, it can happen to sound waves, and it can happen to ocean waves. That is, ocean waves, very long wavelength ocean waves, which are called Rossby waves. If they move in a very choppy environment, then actually they can localize, and of course, this can cause disaster. Okay. Now, this is the sort of final model which I have just said, described very briefly. But how did it come? It came because Anderson was next to an experimental physicist. His office was very close to that of an experimental physicist who was doing experiments on spin resonance. This is George Feher, who was his neighbor in Bell Labs. He developed a new method called ENDOR, which is electron nuclear double resonance, in which he did something very strange, which is, for example, he looked at the okay, suppose there is a complex consisting of an electron and a nucleus, that is an atom. For this, he looked at the electron spin resonance. That is, suppose you apply a magnetic field, then the electron of this atom will have two energies in a magnetic field, and you cause a transition between these two levels by applying a microwave of a certain frequency, which resonates with this energy. So this electron paramagnetic spin resonance was well known by the time Fehr started his work. He applied it to the situation of phosphorus atoms, a small number of donor atoms, donor phosphorus atoms doped in silicon. And the phosphorus electron paramagnetic resonance was what he observed. So suppose you apply a magnetic field and you apply a microwave of the correct frequency, then you can basically hold this electron system between these two states, enable it to make transition from one of the levels in a magnetic energies in a magnetic field to another energy. And when you hold it, at the same time, if the nucleus connected with this electron in the magnetic field which you have applied, if you have an NMR equipment, you make a resonance. Using this NMR equipment, you apply a frequency which resonates with the energy level difference of the nucleus in this magnetic field. So this is a double resonance. And if you do it simultaneously, you can actually use this double resonance to monitor the the neighborhood of the electron spin. That is, see, if the electron is in a particular neighborhood with other atoms and so on, then its resonance frequency will be have a particular value. So by tuning the resonance frequency, you can choose the electronic neighborhood of this atom. Now, he did this experiment and he found something very strange. He found that for low amounts of phosphorus doped in silicon, this neighborhood does not change in time. Now, this could be seen how? Well, it could be seen in the following sense. Suppose the neighborhood doesn't change, the electronic neighborhood doesn't change. Then the electron which has been caught by this Endor method will relax very, very slowly. It will not relax at all, or if it relaxes, it will relax on the scale of several minutes. Now, this is considered very strange because the electron, I mean, let me just show a picture. Yeah, I have shown here a picture of this is a phosphorus atom. This is the best I can do. This circle is a kind of a cartoon for the phosphorus atom electron wave function. The phosphorus nucleus is here. So suppose there are, I mean, I've just shown a very sort of immediate neighborhood of this phosphorus atom. There are 3 atoms in the neighborhood. So this forms a sort of small cluster. So what Feher could do was to basically lock this electron spin orientation, and then he noticed that the spin orientation stays for a very long time. And this is very strange. Why? Because as you can see here, this particular spin is actually in this, for example, this all right, take this atom. This phosphorus atom, the electron here is coupled to the phosphorus atom here, the phosphorus atom here, and phosphorus atom here, which means that the spin of this phosphorus atom electron is coupled to the spin of this phosphorus atom electron, and this spin and this spin. So it is in this way it is coupled to a large number of spins. Therefore, because of this coupling or interaction between these two spins, and many others around, this spin cannot stay pointing in this direction forever. Very quickly, because of this coupling, it will flip. And if this flips, well, the spin with which it interacts, that also flips. So this may be called the diffusion of the spin. Now, the strange thing which Feher observed was that this diffusion does not occur. Why it doesn't occur was not clear at that time. And what Anderson believed was that this doesn't occur because the interaction between this spin and this spin has some value. The interaction between this spin and this spin does not have the same value. It is different. The interaction between this spin and this spin also does not have the same value. So the interaction energies between pairs of spins are random. They have a wide distribution. And maybe because of this distribution, somehow if this randomness is too large, the electron spin here just doesn't change. I mean, it just stays fixed. Now, this is a very strange thought. He got to this stage by ruling out all other possibilities. But this thought leaves you with a very I mean, if you want to say that this is actually not just a plain pure speculation, but it's a real possibility, then you have to actually develop a model which describes the situation. Now, the situation is extremely complicated. You have a whole collection of spins, and their interactions are quite random. And this randomness will lead to the localization of the direction of this spin. So, to model this is extremely complicated. And what Anderson felt was to describe this emergent property of non-diffusion of spin orientation in such a random system. Maybe one should go back a little and think of a much simpler model. And he arrived at or he proposed an extremely simple model in which there are some objects, let us call them electrons. These objects live on the sides of a lattice, which are marked by dots here. These sites are labeled by the index I. If the electron lives on the site I, it has energy epsilon I. The electron, is a quantum mechanical object. So an electron, let us say at this site, the wave function of the electron at this site and the wave function of the electron at this site, they overlap with each other. So this overlap is mathematically described by some number Tij. So this term here describes the fact that you can remove an electron from here and put it there with an amplitude Tij, which is called hopping. Now, the randomness which is central to this phenomenon resides here in the energies of the electrons at different sites. The energies are random, and as I have shown here on the left-hand side, on the right-hand side, the energies at a particular site can range from some value minus V naught to another value plus V naught. And he assumed an extremely simple random form of randomness, that they can range at every site from a value minus V naught to plus V naught with equal likelihood. So this is a very strange caricature of the real randomness in the real system. See, in the real system, the randomness resides in the interaction between the spins. Now, these are spinless objects which are called electrons. Fine. And the randomness in this modeling of the effect of randomness resides not in the randomness in the interaction between them, but in the randomness of the energy of each electron at a particular site. Now, okay, this looks like an extremely simple model in which the randomness is reduced to just a single number characterized by this object. But it turns out that even this model is extremely difficult to deal with. So this shows the way his mind worked. See, firstly, you are inspired by experiment. Then the experiment describes a situation which is pretty complicated, but you believe that the essence of the finding from the experiment resides in a very simple model, and now you try to look at the consequences of the simple model. Now, he showed that, you see, if you have model of this kind, and for instance, this is random, and if the range of randomness this is very small, then the electrons do not sort of propagate coherently from one side to the other, but they diffuse. On the other hand, if this randomness is large, the probability that an electron stays put at a particular site forever is actually non-zero. And this means that the electron can just stay at a particular site forever. With some likelihood, it is localized. And this is the origin of Anderson localization. He showed that if the size of the randomness in relation to the kinetic energy, this is the kinetic energy of motion, if the randomness in the potential energy in relation to the kinetic energy is larger than a certain value, which depends on the energy of the electron, depends on the spatial dimensional space of the system, depends on the lattice type, and so on, then he found that the probability of an electron staying put is non-zero, and this was the origin of localization. Okay, so let me see if I have any time left. If I have, probably a few minutes. Then it turns out that this is the origin of the ideas of localization, and it is actually a very strange idea from the very beginning, because one is used to. It is not that one never knew that electrons can be localized. I mean, they can be localized. If they can be localized, if, for example, there is a potential well. If there is a potential well, electron will prefer to live where the potential well is. On the other hand, here there is no potential well. I mean, at each site, the energy can have some value. It can be positive, it can be negative, it can be large, it can be small. And just this randomness somehow is able to localize an electron. So this is strange, and it turns out it is observed. And as I mentioned, there are a number of examples, not just electron waves, but light waves, sound waves, ocean waves, and as a matter of fact, even tumor localization. You see, suppose you pass sound waves through a breast, looking for signs of breast cancer. Then this sound wave going through the breast, if there is a tumor, then there is a very large change in, let us say, the potential energy there. So the sound is likely to be localized there. And so from this tendency for the sound wave to localize near a tumor, you can actually make some kind of a diagnosis of possible tumors in breast cancer. So, you see how things develop. There's an experiment which is very strange, which is a very strange result, difficult to understand. Then you say that, well, I mean, I don't want to understand this experiment as it stands, but maybe this is the essence of the experimental finding. The essence of the experimental finding can be cast into a simple model, and this simple model can be discussed, and more sort of precisely conditions for observing the phenomenon can be obtained. And then you see that this has a vast variety of applications. Okay, so let me now talk about a few more things. You see, this is since I'm more comfortable with such things, I will talk about another very interesting episode connected with Anderson's work in science, which is the following. Whereas Anderson formulated his ideas of localization in 1956-57 and was awarded the Nobel Prize for it in 1977, it is true that till 1977, there were no detailed experiments which supported this idea in quantitative terms. In 1979, as you heard yesterday, something called the theory of weak localization was developed. This is called the scaling theory of localization, and in this, some experimental quantities were shown to behave in a certain way if localization is impending because of increasing disorder. One of the predictions of this theory was that in two-dimensional systems, that is, in thin metallic films which have disorder, that is so in thin disordered metallic films, the resistivity will increase as the logarithm of the temperature. Now, it is extremely difficult to see from, suppose you measure the resistivity as a function of temperature, you draw a graph, and from this graph, it is extremely difficult to see whether the temperature dependence is logarithmic in temperature or not. And this was, so the measurement was actually done in Bell Laboratories, and the person who did the measurements showed the results to Anderson, and Anderson looked at the curve this way and that way and so on, and said, oh, it's a logarithm. And indeed, if you fit the temperature dependence of the resistivity to a logarithm, it fits extremely well. So this again shows, you see, the uncanny ability to extract something of great importance from some piece of experiment which either is mysterious or maybe whose results may be thrown into the dustbin. There is similarly, Anderson was intrigued in the 60s about the following fact, that if you have a superconductor and if you put some dirt into it, some disorder into it, some atoms you dissolve into it, which are not the same atoms which become superconducting, whose collection becomes superconducting, then you find that the superconducting characteristics such as the superconducting transition temperature do not change. So Anderson developed a general result, which is called Anderson's theorem, in which he showed that if the attractive interaction which results in superconductivity, oh, what happened? Okay, maybe. Okay.
Sir, just go back.
Yeah, I'm going. Okay, let me go back. Nothing works at the moment, but let me. No, no, it's all gone. End of slide.
So you've done, right?
No, I'm not done. I have a few things to say. Okay. Yeah. So let me. What is it? I think the link is broken, and that is the reason why. Share. Okay. No, it's not coming. I mean, I'm doing what I'm supposed to do, which is share.
The one.
Yeah. Fine. Now I'm getting it. Yeah. Fine. Okay, so let me continue. I'm sorry for the disturbance. So Anderson showed that if the attraction which results in superconductivity, attraction between a pair of electrons, which results in what is called Cooper pairs, and then finally results in superconductivity. If this attraction is of very, very short range, then disorder has no effect. This actually cleared up a very big mystery. However, one mystery remained. Oh, what happened again? Yeah, one mystery remained, and that mystery was the fact that when you dissolve a particular atom in a superconductor, whether it has some effect on superconductivity or not depends on the superconductor in which you dissolve this atom. For instance, if iron atoms are sprinkled randomly in molybdenum, superconductivity can be destroyed by a small concentration of iron atoms. On the other hand, if the same iron atoms, which are magnetic, are dissolved in titanium, that has no effect. In order to understand this, Anderson developed a model for local movements, which was described by Dr. Ahluwalia yesterday. Namely, he developed a theory for how an atom, an impurity in a metal, this atom can be magnetic in some, when dissolved in some metals, and it can be non-magnetic when dissolved in some other metals. And this actually explained this observation because if the atom which is dissolved in, say, molybdenum continues to be magnetic, it can be shown that a magnetic impurity in a superconductor is a very bad thing for superconductivity, and it can destroy superconductivity. On the other hand, if the same magnetic impurity is dissolved in some other metal like titanium, if this magnetic impurity turns out to be non-magnetic when dissolved in this metal, then it has no effect on superconductivity. So there was a very peculiar experimental observation which led to a very far-reaching model, which was one of the two things which the Nobel Prize mentions as being crucial for the award of the Nobel Prize to Anderson in 1977. And it turns out that this model is also extremely simplified. It is easy to describe mathematically, and it has far-reaching consequences, as Dr. Ahluwalia pointed out. I think I will stop here, and if there are any questions, I'll be happy to answer.
Thank you very much, Professor Ramakrishnan, for a very exciting talk. Very difficult subject for most of us, but you brought out some of the essential concepts so beautifully, starting with the connections with the experiments in the electron nuclear double resonance, how it led to how he thought about the problem, and the consequences, as you point out, are absolutely far-reaching. This is a great mystery of his brilliance. We will certainly hear about it from Bhaskaran also. But there may be some questions. Let me throw it open to the audience. Any questions?
I Yes, thank you, TVR, for a nice selection. I just want to add one comment on FE in TI. It turns out that small percentage of FE, few atomic percent in TI, increases the TC of TI from zero point 0.3 Kelvin to 1.5 Kelvin. So it is not magnetic, but it does help in a low concentration to increase the superconductivity of titanium. I just want to say that this was done by Bernd Mathias long ago. Thank you.
Any other
Sorry,
question? Yes.
Pranav, I
Yes,
just want to
Bhaskar.
make a comment.
Yeah, please.
After a brilliant lecture of Professor T.V. Ramakrishnan, he mentioned about these applications of Anderson's localization idea. It has gone well beyond physics. Namely, he mentioned about this tumor detection by ultrasound localization. I also heard about it. In fact, I downloaded and I plan to read an article about epilepsy and Anderson localization. Apparently, if you think about neural network as some kind of wave, some brain wave is propagating, those waves also get Anderson localized, and that can explain epilepsy. Amazing how things have gone way beyond the beginning, whatever it was started
Yeah.
with.
Yeah.
Thank you.
Right. I also wanted to mention that, but then I stopped because it is not experimentally verified, whereas this tumor localization is actually something which doctors use.
Thank you.
Sir, I have a question, basically, that this Anderson model of local movements, does it apply to thin films, or is it for bulk as well, polycrystalline, or every kind of material that we prepare in a lab?
It applies to everything.
Okay, okay. Thank you, thank you.
His comment more is different. Did he go as far as speculating on issues like consciousness?
Yes, I think in one of his essays, Anderson says that consciousness may be the ultimate emergent property. However, I think in this his belief is exactly the opposite of the traditional Indian belief, which is that the consciousness is the fundament, and from that arises all universe, including the material universe.
Yeah, of course, right. Yeah, I think your exposition of the mechanism of emergence in his thinking is pivotal to how he worked on these problems, starting with something very simple, but coming up with models which explain fundamental things in nature. It's a beautiful talk. Thank you very much, Professor Ramakrishnan. We will now.
May I ask one question?
Yes, of course, Professor Ahluwalia.
Thank you very much, Professor Ramakrishnan, for that thought-provoking. I think it should really set us thinking about many things around us. It took us beyond physics, I would call it like that. And but there is one question which was coming to my mind, and today, these days, we know a lot of us are talking about everything being done under ab initio kind of things, ab initio calculations, and we are hoping that on the computers we can really, starting from the minimalist things, we can arrive at all the answers. So what do you think about it?
Well, I only can say what Anderson thought about it at the moment, and this is what I would like to say. Anderson felt that such a perfect calculation reproduces nature but does not explain it.
Thank you.
Very, very beautifully said. So it's a very telling statement. Any other question or comment? Anybody? If not, let me thank Professor Ramakrishnan for a brilliant talk, very thought-provoking. I'm sure questions will keep coming. But let me invite Professor Bhaskaran to explain to us the secret of Anderson's success. Bhaskaran?
Yeah. So I'm trying to share the screen. So I have pressed the green share screen.
Yes.
One participant can share at a time, I think. TVR has to unscreen.
I have unscreened.
Okay, then. So what do I do? Let's see. Do you see my screen?
Not yet.
Not yet. Do you see my screen now?
No, sir. Yeah, now
Yeah,
it's
you know,
coming.
It has
yeah,
come.
absolutely. We see your screen.
Yeah. You can go full screen.
Full screen. My God. The full screen disappeared.
Yeah, I think that slideshow might do it.
Slideshow. So I'm slideshow. Nothing is there.
Oh.
My God. So what I could do is, if you permit me, we can proceed with this. Is it okay? Is it too small?
No, it's fine.
No,
Except
it is readable. If there is magnification available, you might use it. But otherwise, it is not bad. We can see the slides.
Sir, on the top, there are screens, 1, 2, 3 screens there. If you touch on that, maybe it will do the trick.
Okay. So let me proceed.
Yeah, sure.
Shall I proceed?
Yeah, please.
Okay, good. So, after these three wonderful talks, two by Ramakrishnan and one by Ahluwalia, secret of Anderson's success is no more a secret. So you heard how he works and so on. So what I plan to do is, I will go along those lines, and then whatever impression I have, I will share it with you the next 45 minutes or so. So this is Phil Anderson. I took this photograph. I'm very proud of it. He's looking at flowers from his office in Jardin Hall. And then this is my institute. Now I have no time to talk about my institute, except that I will show you. Math Science is a very beautiful small campus. Then if you come to Math Science, we will take you to just 2 miles from Math Science. You have this beautiful seashore. You can see auto rickshaw. There's a busy street on the one side and then Kamsi on the other side. You go in the morning, you can see this beautiful fishermen catching fishes. I took this picture a few years ago. If you come to IIT Madras, it's even more natural. There are deers and monkeys and students and professors running around. Then I also work at Perimeter Institute, which is a beautiful campus. So I just wanted to show you that when education institutions are located in natural surrounding, it's much more exciting and it's very useful. Huh? Sorry? Do you hear me? Hello?
Yes, sir, we can hear you. Please carry on.
Okay, shall I proceed or?
Yeah, yes, sir.
Okay. So then this Perimeter Institute is something special because Mike Lazard is a BlackBerry chief. He has donated started with $150 million. Now he has given about $400 million. He says theoretical physics and open-ended research in science is something that will help transform society. We have heard such people in India also. So I have been propagating the idea that we should depend on research for fundamental research in India more on private donors than on government. Anyway, that will be a separate thing I will talk about if necessary. So we have heard about great scientists Newton, Maxwell, Faraday, and so on. And then here is Van Vleck, Mott, Bodin, Cooper, Schaefer, Anderson, Cohn, Leggett, Parisi, Hopfield. I have not seen Van Vleck and Mott, but I have seen the rest, thanks to association with Anderson. So matter is quantum. Whether you take a piece of rust, or a grain of sand, or a drop of water, or a paisa coin, everything is quantum. Why I'm showing this is because Anderson's work, for example, he worried about origin of magnetism in metal. There is something called double exchange, Zener's double exchange, Anderson-Hasegawa mechanism. Similarly, if you take a rust, supposed to be a hot insulator, Fe2O3, hematite, then grain of sand and minerals, even though it tells about geological history, they are amorphous and glassy material. Lots of physics was started by Anderson about that. Similarly, if you take a drop of water, there are electric dipoles, hydrogen bonds, and quantum pairs. Water is supposed to be quantum paraelectric. And if you take a copper paisa coin, and if you add magnetic impurities, something interesting happens. T.V. Ramakrishnan mentioned sometimes magnetic impurities retain their magnetism, sometimes they don't. And then if you form a compound with copper, like lanthanum copper, it becomes superconducting. So this was Anderson's amazing thing. So again, you heard about it before. Anderson was born and he had a wonderful time as a young child. A lot of hiking and Saturday hikers. And then, they were very politically conscious and lived in campfire, vacationing and picnicking, singing and so on. It's already seen even in this picture. This was a picture taken by my former student, Muthukumar, who became a professor later. So Muthukumar took this picture of Anderson in Kathmandu. And Anderson suggested call it physicist at work. Imagine Anderson laying on a big piece of rock, and he doesn't care about the hard thing that he's sleeping on. He's laying down. So that is Anderson. So he had undergraduate studies in PhD at Harvard. You have heard about it. What is interesting is at excellent courses, delightful group of friends, centered around bridge, puzzling, and singing. He was a happy man. So I always tell students, be happy, have lots of friends when you are a PhD student, and they know about what the others are doing. It's very important. When you share your knowledge, fantastic things happen. In fact, Anderson is supposed to have drawn into NMR and so on because he talked to students of Van Vleck and others who were doing experiments or at some other group there, I think. Then Anderson married Joyce, 73 years of lifelong journey. A wonderful couple and great hosts. TVR knows that. Joyce was a great support for Anderson. Their daughter Susan, an artist, lives in Boston. So this is a picture. Thanks to Anderson, Ramakrishna, I got this picture. Then a secret of Anderson's success is another thing. At some point, Anderson and Joyce moved from Bell Labs area and got a 10-acre land near Princeton called Hopewell area. It's a small village called Hopewell. So 10-acre land. And Anderson and Joyce took care of the entire estate. They used to work for 4 hours. Joyce used to work for 4 hours every day or 5 hours. Anderson used to work for 3 hours in the morning and then come to the lab to Princeton. So I think that is the secret of his success because he remained healthy. He was looking at nature constantly and looking at birds, hearing bird songs, looking at flowers and so on. So now we have already heard about Anderson's and how kind he was. So I just want to narrate a personal incident. It was in 1986. I was sitting in his office and an undergraduate student walked in. Students knew that no prayer appointment was necessary to meet this Nobel Laureate in his office. The student elaborated on an idea he had. Anderson noticed my growing impatience. He, however, patiently listened till the end. After the student left, Anderson enlightened me with his own understanding of a very important point that the student was actually trying to convey but didn't succeed. That awoke me. You can see Phil Anderson discussing with Muthukumar, Manas Sardar, Indrani Bose, and Mukul. Intently, he's listening to some ideas from the students. That is Anderson. And on several occasions, it was said that Anderson brought out deep meanings in very ordinary sounding seminar talks and pleasantly surprised the speaker and audience. It was said that Anderson's presence made a difference to conferences, workshops, and schools. He alerted colleagues about key developments reported in the meetings and shared his ideas liberally. Anderson was amazingly supportive of his young associate. I will tell a personal anecdote. While at Princeton, I faced some issues renewal of my US visa for third year. The news reached Anderson. He told me, I'll call George Shultz and fix it up. George Shultz, incidentally, was Secretary of State of the US government and a Princetonian whom Anderson knew personally. I felt elated but politely stopped Anderson. That particular problem got sorted by Anderson's secretary. The third year at Princeton became a memorial period in my scientific career. So that's Anderson. Now, I should also, since I'm talking to the physics teachers and students, it's very important to tell how others help you. You are not on your own. You are just lifted up by others. For example, as I said yesterday, I listened to 2 talks in Madurai DI Symposium in 1970 when I joined IAC. Fortunately, the DI Symposium was in my hometown and it was held in the college where I did my master's. So I listened to a beautiful talk on Majumdar Ghosh model. The proof of that, the ground state, valence bond solid is a ground state by a short talk by Pasupati, and spin fluctuation theories. Then in Bangalore, IASC, Narendra Kumar was excited about Anderson localization theory, Mott localization, and super solid helium-4. And Professor Sinha, who had joined IASC from Bell Labs, he was talking about super exchange theory and stories about Anderson. And Rajaram Nityananda, who is at ICTS now, amazing guy. He was 1 year senior to me. But he taught us about Anderson localization, local moment formations, and heavy fermions, and a variety of things. And we had S.K. Rangarajan, who encouraged us to have after-group dinner discussion in his house. So that was the atmosphere at Bangalore. And I learned from Sriram Shastri, a good friend. He is my contemporary, but he did his master's at IIT Madras. Then we met in a summer school of Tata Institute of Fundamental Research at IAC Bangalore. So we became friends. He explained to me how quantum fluctuations create a spin liquid in 1D Heisenberg antiferromagnetic chain. He didn't call it as a spin liquid, but it was a spin liquid. And Chandra Verma, one of the speakers, talked about Hubbard model and Anderson model. And Acharya Krishnamurthy, when he joined IAC, he taught me about renormalization group approach to local moment problem. Then I became a fan of Anderson. In fact, I ran a journal club. It was only Anderson's article that was discussed. I had a dream. I will not tell it now, but later. And then ICTP, about which I'll tell soon. I had the wonderful chance of knowing Patrick Fazekas, who started RBB theory with Anderson. So then also, because of that, I was reading Anderson's paper just before RBB theory started. Now, I should mention about Professor Salam, a great man. He, in some sense, was responsible for the development of theoretical physics in China, India, and so on. Now we were very independent, but 60 years ago, when ICTP was started, that played a very important role in the development of theoretical physics. In fact, I met all my theoretical physics colleagues for the first time in ICTP. For example, Arun Grover and S.K. Joshi, Pathak Saab, many people, maybe even Sharma in ICTP. And that's a fantastic story. In fact, I wish that Indian IAPT has some session on how Salam influenced theoretical physics on some future occasion. Then Anderson was a great friend and supporter. He visited ICTP regularly. So when I was there, I was spending 3 years. 2 years at ICTP because I lost my job in Madras and I went to ICTP. I met Anderson. It was Eriot Tosati who pushed me to talk to Anderson, and we had a fight actually, Anderson and myself. And then that's how my association with him started. And fight means I was saying that super solids exist. Anderson said they do not exist, and so on. We had a wonderful time, 2 hours of intense discussion. Now I come to Professor Ramakrishnan and Ahluwalia talked about various contributions. I have put Anderson's contributions in the form of a Tower of Anderson model and theories. Theory of spectral line shape was his PhD thesis, which is a well-known work, which was also independently done by Kubo, which made him very famous. And his notion of spontaneous symmetry breaking, Verbi transition, super exchange, body of everything is experimental motivated. And then some of them I have put double star. That means his work is responsible for others' Nobel Prize, like BCS theory and Anderson pseudo-spin model basically led to Josephson effect and so on, understanding. Then Anderson issue on gauge invariance and Anderson-Higgs phenomena became a mechanism for mass generation of elementary particle, Nobel Prize for Higgs. Then local moment in metal and Anderson, he got Nobel Prize. Then spin glasses, recent Nobel Prize of John Hopfield, is you can trace it to Edwards Anderson model and Sherrington Kirkpatrick model, and also Giorgio Paris's work, Nobel Prize a couple of years ago. Then similarly, Anderson model Brinkman phases was responsible for superbluity in liquid helium-3. So then variety of things. So it's amazing that a single man can do so many things. So now, it was a meeting in Aspen in 2000. We were honoring Anderson 50 years of contribution to condensed matter physics. I began my talk and told the audience that before I begin my technical talk, I will give you a model for Anderson's secret of success. Anderson was in the audience, raised an eyebrow. You must have thought what this chap is going to tell. So I said the obvious thing, keep looking at experimental results and contemplate. You will discover the right model. The model is his brainchild. However, often Anderson cannot solve the model. Even finding approximate solutions becomes challenging and formidable. Sometimes there are too many possible solutions. Hilbert space is incomprehensibly vast because we are talking about many-body Hilbert space. Then what does Anderson do? Anderson goes back to experimental results, looks at them again and again, and contemplates. Experimental results suggest him physics-guided mathematical approximations to find correct solutions to the model that he has invented. My statement actually got a smile from Anderson. Approval smile. So that was Anderson. And Anderson has a very nice article which appeared in Physics Today. Some thoughtful words, not mine, on research strategies for theories. It's a wonderful article where he basically quotes the one-page article in Physics Today, where he quotes famous Crick of Watson and Crick's, double helix famous, how he talks about theories, role of theory in biology. How, in some sense, we have to be very, very open-minded and be ready to change your theory anytime. Because nature is supreme, a theory has to agree with nature, and the theories are often caricatures. They are simple caricatures of reality, so they can be wrong. So it's a wonderful article by Anderson. In fact, I will give some examples later. Now, this became very clear even at the beginning when Anderson joined Bell Labs. Anderson believed in the importance of thinking in generalities. In fact, I think Ahluwalia slowly alluded to it in his early talk. So Bell Shockley, a tough guy, had an idea about barium titanate. He wanted young Anderson to do some detailed calculation. Anderson says, so he resisted any calculation. He says, soon I became more interested in general phenomena, feeling that calculations were premature. This is an important lesson in doing science. While acting locally, one should not forget to think globally. So that in fact, I remember once he remarked to a friend of mine, we were traveling in a car. The problem with you is you start calculating before you start thinking. Think before you ink. That is Anderson's message. And it's also part of Bell Labs culture. Of his formative period in Bell Labs, Anderson says, and I learned most of all the Bell Labs mode of experiment, theory, teamwork. Two of the motto of Bell Labs, get the best people in the world and get out of the way. Theory should be on top, not on top. Yesterday, we were already mentioned about it. Okay. So already you have heard about this local moment formation just from TBR. I'll repeat it. Maybe it's worth repeating. So what did Anderson do? So there are body of experiments, including the experimental results on superconductivity, like TBR and Ramke also said. We take titanium and put iron, doesn't form a magnetic moment, so the TC even increases. Whereas you put manganese, it kills TC. So there is something. So why iron loses its magnetic moment in titanium, or why manganese retains its moment? So it's a challenging problem. So this Anderson looked at body of experimental results. Then there were earlier insights like Friedel's phase shift, Friedel's sum rule, etc. But Anderson couldn't solve this model, so he wrote down a model, but didn't realize the treasure it contained. Encouraged by a body of experimental results available, he performed a Hartree-Fock analysis and obtained qualitatively the right answer for certain results. Then, even then, Anderson did not understand the meaning of his model and the consequences. Help came from friends. Kondo said that there are these fantastic anomalies in resistivity called the Kondo minimum. He said that it comes from scattering of conduction electron, spin flip scattering of conduction electron by local moments. So then Anderson said, in addition to local formation, something subtle is going on. Then help came from other friends, Majumdar and Kohn. They were also puzzled by experimental results. What they did was, they did a very simple model in which they put an impurity, put a scalar impurity, then found that the physics was continuous, particularly energy was continuous as a function of coupling constant. So they said nothing dramatic happens. Now, it is here Anderson had a different viewpoint. So it's like standing on shoulders of giants. So what Anderson said was, yes, energy is continuous, but if you look at the wave function carefully, there is a catastrophe. That means when you put even a tiny impurity in a metal, in a localized impurity, the many-body wave function becomes orthogonal to what it was in the absence of impurity. So that's called Anderson orthogonality catastrophe, coming from soft low-energy excitations that is possessed by Fermi-C. In fact, this is related to infrared problem in quantum field theory also. So this is the beginning. So Anderson did not realize all these things when he did his model. Slowly, with the experiments and trying to understand others, he got it. Now, Anderson's orthogonality catastrophe theory provided new insights and development. For example, it solved the problem of X-ray singularity, Schiefer-Wolf transformation, Kondo effect, Anderson-Kondo lattice, heavy fermion, hidden Fermi liquid theory of normal state. Then he went further and did Ewell-Anderson scaling, which led to Kostelis-Thouless BKT scaling, then a model for asymptotic freedom, and so on, a variety of things. So this is the power of Anderson's model. Its applications give immediately, because it contains some essential physics, key physics, which is surprisingly valid everywhere in many other places. So this already TVR mentioned about, so I will not elaborate on it. Absence of diffusion and random lattice. And now I just want to point out that Mott used it to understand mobility edge, and he introduced the notion of mobility edge, and then famous theory of Abraham, Anderson, Richard, and Ramakrishnan, scaling theory of weak localization, which emphasized the physics of coherent backscattering, very important point. Then now it has gone to light waves and classical waves and epilepsy and so on. So recently this field is revived by many people, friends working in India, abroad, many-body localization, quantum scars, and Hilbert space fragmentation, which may have some new implications for quantum computing. Okay, now let me talk about another theory which was phenomenologically motivated by Anderson. Anderson had great respect for Linus Pauling. So Linus Pauling was an amazing empiricist, as they say. He wrote his book on nature of chemical bond even before quantum mechanics was completely formed. So with chemical bonding, with simple idea of sp bonding and hybridization, he did wonderful work. So he went to benzene, which exhibited some peculiar diamagnetism and many aromatic rim compounds and so on. So Linus Pauling introduced the valence bond resonance and resonating valence bond state. Now, Linus Pauling went overboard. So he overused this idea and he said that, again, I explained lithium metal and so on using RBB theory. I don't need Fermi surface physics. I don't need Fermi surface. It's useless. So that's when Anderson got alert. Apparently, Pauling, 2 times Nobel Prize winner, great scientist, has very strong opinion. I can personally vouch for it, because in 1987 March meeting, when high TC superconductivity became very hot and RBBT was and so on, there was a beautiful talk by Linus Pauling on quasi-crystals. So I remember Linus Pauling's statement, there are no quasi-crystals, there are only quasi-theories. He said there is nothing like a quasi-crystals. Everything can be explained by twin boundaries and a collection of them. So he was so emphatic. But of course, Sheckman and others got Nobel Prize 4 years later. So that was Pauling. He had very strong opinions. Then Anderson became aware of the work of Pauling in the context of lithium, and he said, Professor Pauling is overdoing it. And already Anderson was very worried about a very different phenomenon, namely absence of long-range Neal order in several spin-off magnetic insulators, not insulating oxides, or high sensitivity of T-Neal to disorder. This is something that Anderson knew from his talking to experimentalists in a variety of phenomenology. He realized that quantum fluctuations of interacting spin-off moments are playing a special role. In fact, apparently even Landau believed that spin-off moments will have such a strong quantum fluctuation, they will not have long-range order. So what Anderson did was, he gave a healthy criticism of RBB theory of Pauling, and he submitted a paper in honor of Pauling's 60th birthday. Of course, the paper reached late. So he said, Professor Pauling, your states are more relevant for describing magnetic states of spin-off Martin-insulating antiferromagnets with vanishing TC, rather than for lithium and other metals. And also it may be relevant for organic. He didn't question that. But he said there is a whole body of oxides which are behaving in a peculiar way, which are Martin-insulators, and your theory will be relevant there. So in order to illustrate the idea, he took this spin half Heisenberg antiferromagnet on a triangular lattice, which he pointed to as frustration, because there is no absence of 2 sublattices, there are 3 sublattices. There is no way by which you can have Ising order. But if you try to do spin wave theory, you don't get divergence and so on. So Anderson realized that somehow the spin-off quantum antiferromagnet should be closer to disordered state. So he didn't know how to. But Anderson did not get frustrated. What he did was, he used Pauling's RBB wave function. He just wrote down a ground state wave function involving nearest neighbor singlets of various configuration and coherent superposition, and immediately talked about absence of long-range order and some properties. He did not, in fact, this is Anderson's great thing, he did not comprehend full meaning and implications of his own wave function for Martin-insulator till Bednar-Muller's discovery alerted him in 1986, which is what I will tell tomorrow. So he had to wait for nearly 73 to about 15 years to be alerted by experiments again to say that he has actually showing a new direction. I will talk about it tomorrow. Now, at this point, I always want to tell young friends that however unrealistic they may be, solvable models have great merit. In fact, I gave a talk in SN Bose Center some years ago honoring Chanchal Majumdar's Remembrance Day. So I said that merits of simple models. For example, if we take Edwards-Anderson model for spin glass, which was done by Sherrington, just take a bunch of spins and couple every spin to everybody else and make the coupling constant form a Gaussian random distribution with some mean value. And then it doesn't look like describing reality, it's a caricature. But however, It led to optimization problem, ultrametricity, Nobel Prize for Parisi, and Hopfield's network recently, neural network theory, and Nobel Prize. It's amazing that the insights that Anderson and Edwards provided have implications for machine learning, the artificial intelligence, which is ruling the world now. In fact, you should talk to Vipin Srivastava, who is in the audience, to learn more about Hopfield's network, and he has done a lot of work on it. Then in the wake of this, Sachdev and Ye wrote a quantum liquid model. In fact, that was a very unpopular model because it was very heuristic and unrealistic. It didn't have a lattice and so on. Everybody was connected to everybody else. So it was an exactly solvable algorithm model. However, so not many people looked at it except for Anton George. Then it fell into the hands of Kitaev. He looked deeply into it. He simplified it and replaced fermions by Majorana fermions. He found that it is actually illustrating the deep phenomenon of black hole thermalization and ADS correspondence and so on. So SVK model is the most cited model in the recent past. Three Nobel three papers by David Gross, a Nobel laureate, and three papers by Ed Witten, a Fields medalist, and so on. So it's amazing, however unrealistic they may look like, solvable models have great merit because they take you to new domains of mathematics and so on, and eventually to physics. So this is my advice to young people. Please, if you can find your own solvable model, please don't give it up. Then having said this, I will also want to talk about Anderson's great quality, how he plans seats for Nobel Prizes. I will give three instances. In the same meeting that I was mentioning about 50 years of contribution to condensed matter physics, in fact, TVR was there in that meeting, we were all together. He has often guided experimentalists to the right path. This also. So Doug Asaraf, a Nobel laureate, and Dan Sui, they spoke at the meeting. And Doug Ashraf, after a PhD from Cornell, or Chicago, he was a postdoc at Bell Labs. He saw some glitches in his data when he analyzed liquid helium at millikelvin temperature region. Then he went and showed it to Anderson. His bosses, they were not impressed by it. They said there may be some noise and so on. Anderson looked at it this way, that way, and said, my God, we have predicted superfluid phase transition around the temperature. Please look at it carefully. So that's the beginning of a Nobel Prize. So he discovered it. So Doug Ashraf got Nobel Prize. In fact, Doug said that I owe my Nobel Prize to Anderson. Then comes Dan Sui, who is a professor of electrical engineering department at electrical engineering at Princeton University. There was great excitement when integer quantum Hall effect was discovered by von Klitzing. So Dan was a great semiconductor guy, so he had better samples. So he wanted to reproduce integer quantum Hall effect in a better sample. And then he not only noticed integer quantum Hall steps, he in between he noticed some small step-like features. So he went and he was convinced that it's some experimental artifact. Anyway, he thought he will talk to Phil. He took it to Anderson and showed it to him. Anderson thought for a while, my God, please look at it carefully. There should be steps there. He didn't say anything else. So Anderson Dan Sui went back and did careful experiment, found fractional Hall effect. He got Nobel Prize. So Dan Sui also said that I owe my Nobel Prize to Anderson. So that's the way he understands experiments and also pushes it. Story of Josephson effect, many of you may be familiar with it, so I don't want to bore you with it. But while at Bell Labs, Anderson had a joint appointment with Cambridge University for a number of years. In 1962, in his lecture on many-body theory at Cambridge, Anderson made a passing remark about anomalous current between two weakly coupled superconductors as a consequence of BCS theory. He is supposed to have written down the current between the two superconductors, if they have phases phi1 and phi2, will be J equal to J0 cosine of phi1 minus phi2. And rubbed it off. We forgot about it. Brian Student, a student of the class, took Anderson's suggestion seriously and proved the existence of such an anomalous current using BCS theory and showed it to Anderson. Anderson was very excited and encouraged young Josephson to publish it. Then there is a story behind it. I will not go into the details of how John Bodin was negative about it and then it changed. So most remarkably, after returning to Bell Labs that year, Anderson and his experimental colleague John Rowe performed an experiment that demonstrated the Josephson effect, thereby removing widely prevailing skepticism in the community about the possibility of such effects. The rest is history. That is Nobel Prize for Anderson. So, that's why, this picture is there in Anderson's office, where he is asking, what shall I plant next? So, each picture, for example, the one behind is supposed to be origin of magnetic field in neutron stars. So it was conjectured by Anderson, and the people knew that there are superfluid neutrons, and then Anderson, there are vortex lattices. These vortex lattices move, and that produces the glitches in pulsar timings and so on. Then Mott localization, Anderson localization, and there is something called motional resonance. When the first work of line narrowing because of motion, the first work of Anderson, that is required by this B. Okay. Another important thing about Anderson and his greatness in supporting others is BCS theory appeared in the scene around the end of 1980. It caught the attention of young Anderson, who was worrying about magnetism, many-body localization, later called at that time. Then Ted Schultz, who was at IBM, my old friend, told me the following story in the summer of '89. Body and Cooper shear theory had just come out. It was getting a lot of attention, but not completely accepted yet, partly because of the issue of gauge invariance issue. News of BCS theory reached Pauli in Switzerland. Apparently, Pauli was a good friend of Van Vleck. Van Vleck was Anderson's supervisor. So Van Vleck has told a lot about Anderson. So he was quick to ask what young Phil Anderson felt about it. The answer was that Phil Anderson was excited and was working on it. And Pauli is supposed to have remarked, then BCS theory must be correct. That's the level of Anderson's thing. And also at that time, I want to mention another great man making a remark about Anderson's work. Anderson, after his work on soft mode theory of ferroelectricity of barium titanate, he goes and presents it in the famous Landau seminar at Landau Institute in Moscow. And because Gorko told me once about it later, Anderson also told me that Landau seminar is supposed to be notorious in the sense Landau will ask very tough questions and will not allow the speaker to proceed and so on. And Landau was so impressed by Anderson's work, he kept silent. So Anderson writes in his book that that's the greatest merit that I can get. Okay. Then another thing about how others benefit. So in order to explain the BCS theory and gauge invariance issue, Anderson found out what is called the Anderson-Higgs phenomena, in which the plasmon can be thought of as a mass generation issue and so on. I will not go into that. That is the Goldstone mode of a superconductor. In a neutral superconductor, gets hybridized with plasmon and becomes a Higgs mode, a massive mode. So there is a beautiful article about it by Ed Witten in the PW90 Life Organisms on Anderson. And then I was at Princeton 3rd July 2012, a day before Higgs discovery was to be announced by CERN. I was visiting Anderson at Princeton. Physics department was jubilant because of the impending announcement of discovery of Anderson-Higgs particle. Anderson told me, I'm happy that Peter has found this. Now he started asking, anyway, so he started asking, is Higgs field a collective mode of some Fermi has CERN determined spin and other quantum number of Higgs particles? Physics kept Anderson happy till the end, actually. This is a picture. I had this with, I think, Fonang, my friend, took this photograph. We're discussing about it during tea. So I have written specifically 3rd July. So it's a memorable year. Then, how much time do I have, Pranav? Hello?
That's okay. I think you have another 10 minutes.
Okay. Good. I'm worried about people, leaving. It's 8 o'clock and they will have
No, it is
dinner and so on. So I will finish quickly.
Yeah, it is. There is 10 minutes to 8 now. 8 minutes.
Wonderful. So I will finish in 5 minutes and then give some time for questions. So already we talked about triangular lattice antiferromagnet. If it is an icing antiferromagnet, there is a frustration as explained here. That is, if you take a square lattice and look at 4 spins, each spin can organize itself in a way, same way that every bond is happy, every bond is antiparallel. Whereas if you have 3 spins which are from an equilateral triangle, there will be always one pair which will be unhappy. That's called a frustration. In fact, that name I think, came in a leisure school when I think Toulouse introduced that name, and Anderson said frustration is the name of the game, and it got stuck to that field. So this is again an experimental fact. In a number of solids with moments, their spatial arrangements is such that some spins interact ferromagnetically and some antiferromagnetically. Intrinsic frustration is there. It is obvious that the arrangement freezes into certain pattern below a sharply demarcated temperature. These are spin glasses.
I was just actually I had messaged you also.
Yes.
बहुत देर हो गई तुम लोगों को.
Sorry, you have sent me a message. What is the message, TVR? Will you please tell me? Because I don't know how to see the message. Hello? I think am I audible?
Yes, sir, you are audible. I think he is talking to somebody else.
Oh, I see. Okay. sorry. Okay. It's a crosstalk. Okay, good. So this was an experimental fact. In fact, many people were working on it. They put a little bit of magnetic impurity. There is no long range, but there is some rigidity of the order. So Edwards and Anderson looked at it, and they said, what is important is rigidity. You look at a spin, it may not have a order with respect to neighboring spin, but it's fluctuating about some random direction. So rigidity as opposed to long range order is the key thing. So they developed replica formalism and so on, and Parisi came and solved it in a beautiful way and got Nobel Prize. Then Hopfield used it for neural network and got Nobel Prize. So now let me. So the construction of new algorithm and computational scheme for hard combinatorial computing problems was something that attracted Anderson after Hopfield did this work. In fact, when I was at Princeton, we did some work on traveling salesman problem and so on, and then some with Danstein on other three-sat problem. So it became models for protein folding and conformational dynamics. In fact, maturation of the immune response, prebiotic and biological evolution, neural network, new methods, and so on. So science of complexity had its origin in some sense through very dirty looking material, namely spin glass. You take copper and put some magnetic moment, then it starts exhibiting some very funny magnetism, not long range order, spatial order, but some rigidity. A careful look at it, and a proposal of a Edwards-Anderson model opened a door for new development. So this is what Anderson calls it, more is different. In fact, it was beautifully illustrated by the 3 talks that you have heard so far. So let me see what I have next. Okay. Anderson also had, it's very important to mention this because I was mentioning it in a meeting in Calcutta. See, in some sense, in India, we are very unwise. We kick out people at the age of 60. Serious scientists who are not yet reached that peak, because these days science is becoming so complex. So you need some maturity to do great things, maybe 70 and so on. So, but at the age of 60, you retire people. And now there should be opportunities for those who want to pursue science to pursue it, but there is no such opportunity. So Anderson has a very interesting thing to say about it. In fact, I used it in a recent meeting in Saha in SN Bose Center in the context of Bose centenary paper. So many people agreed with me. No one does anything original after the age of 35 and the like. He says the cliche is wrong. Everyone has an age at which he stops thinking originally, but that age is enormously variable. I know plenty of others who haven't reached it at all, 80 or more. So physics has remained exciting and wholly absorbing as I age. This was P.W. Anderson's statement in the preface to his book, More and Different. In fact, Shobana Narasimhan, our colleague from Jawaharlal Nehru Center, she has a very interesting article. In fact, when I saw that her article, I told her Anderson's work. She was very happy. Age-old question about age and retirement. I want to point out, because this is important. Then this is something, see, Ramke is in the audience. They discovered something very beautiful in 2017, namely bismuth, elemental bismuth, which was never suspected to become a superconductor, became a superconductor, half a millikelvin or some low temperature. The world record, it's the second lowest TC material. So I got very excited about it, and I wrote an article with the title Tip of an Iceberg. I gave a talk about it at Princeton. Anderson liked my idea. He supported it. In fact, then he called me to his office and he said, "Here is a gift for you." Then he gave me this structure, which is supposed to be the structure of bismuth, some distorted FCC lattice, called, I don't remember the name of the structure. And it was given to him by Gregory Vanier when they were roommates at Bell Labs. So Anderson approved the theory. Unfortunately, he's no more with us. Okay, then let me complete. With the last few slides, I visited Anderson in December, and on 13th December I was there. We had a meeting. I alerted the friends at the physics department that it is his 95th birthday. So we had a wonderful time talking about physics and fun. And this is a picture I had with Phil. And then he remarked at the end of he was passionate about physics. Bhaskaran, he made an interesting remark. You and I understand theory of and mechanism of Q-period superconductivity so well. I wonder why others don't understand us. So we laughed spontaneously, and I said my last goodbye. So that's it. Thank you very much. And I'll be happy to answer any questions.
What an amazing talk this was, Bhaskaran. Thank you very much. I'm sure there are some questions from the audience, so let us go to the audience first. Questions, comments? This is turning out to be a wonderful celebration. Means
so it's there after the talk is over. So it has been always there in the background. It looks like that.
Bhaskaran, it was an amazing talk.
Absolutely.
Such a sweep you have presented. I mean, it's just, and I think I must thank you that you have presented it before an audience of Indian Association of Physics Teachers, because I think we must keep on reminding ourselves about the opportunities which are available to us. And these are very, very inspiring moments for IAPT, listening to the talks of Professor T.V. Ramakrishnan and Professor Bhaskaran. I have no words to express my thanks to you. What a wonderful journey you had. I think that's great. Thank you very much.
6 hours.
No doubt the greatness of Anderson, but I don't think it could have been brought out so beautifully without the greatness of the three speakers. Ahluwalia, yourself started this lecture series so beautifully. 2 talks by TVR and now Bhaskaran's. We have had a wonderful time these two evenings. So Bhaskaran brought out the beauty of solvable models and how far one can go with these. I think very beautiful illustrations throughout these talks. Any other question or comment?
Yeah, can I?
Yes, Vipin, please.
Yeah.
So, well, this was a stunning talk, actually, Bhaskaran.
Yes, it was.
And see, you made an excellent point about solvable models. And in that connection, I would like to remind everyone that Anderson's model was proved to be very difficult to understand and solve for several years, since 1957 until early 1970s, when Thouless gave an exact solution of, for Cayley tree.
Yeah.
He truncated the normalized perturbation expansion after the first term and solved it exactly. That gave a great impetus to the research on Anderson localization, as far as I can think. So that's a very good which one should, a lesson one should take from your lecture. So thank you. Yeah.
I forgot to mention one thing. See, I was in Shimla not long back, 1971.
Okay.
1971, I came for a summer school organized by Delhi University on statistical mechanics.
Yes,
In fact,
sir.
I had the pleasure of listening to Professor Terhar. So
Yeah.
I don't remember exactly where. I was there for 2 weeks. I had made many good friends. So I wish I could be there, really there. I'm only virtually listening to, I think some of you are in Shimla, sitting in Shimla.
Sir, you are welcome. Anytime you come, we welcome you there. And there is a collection of articles of that school available in our library, edited by D.T. Harsh.
Oh, yeah, I see. Wonderful.
And that was actually the beginning of our physics department in HP University. And
Okay.
D.S. Kothari was very much, interested that there should be a theoretical group established in Shimla. And
Okay.
that was the reason that that school was actually organized there. So it's
I was a participant in that school. I had memories. Fantastic.
Thank you.
I have one more question.
Tail end, 5 minutes.
Sorry, TVR is asking something. So, see, you told that Anderson's daughter is an artist.
Yeah.
And you also told about his proximity to nature and that big
land, yeah, estate, yeah, 10 acres land. Yeah.
That he developed. Now, did he have interest in any of the fine arts like music or painting or anything?
Oh yeah, in fact, that's interesting. He was interested in observing nature. I think that was his. He was not a musician or a painter, but he enjoyed looking at. Well, as I said, every day he used to work for 4 hours in his garden, maintaining them. So that is like our farmer, he was enjoying that. But unlike Einstein or Bose, he was not playing any instrument. But whatever Anderson said is a music to our ears.
That's a good one.
Very beautifully said, Bhaskaran. What a wonderful evening it has been.
Yeah.
Maybe Dr. Sapna.
Yeah. Yes, sir. Yes, sir.
So,
Yes.
ma'am, I want to give a comment.
Yes.
I really feel blessed to have heard these people, and I really feel blessed to be a part of this platform. So thank you very much, sir. All the three speakers are really awesome. Thank you.
Thanks.
Yes.
Thank you for saying that, because what you just said must be the thought of everybody in the audience.
Yeah. Yes.
Thank you, Sapna.
Definitely. Yes. So thank you very much, Professor Ramakrishnan. Thank you very much, Professor G. Bhaskaran, for sharing your experiences and expertise with us. And it was truly a pleasure to hear from both of you. Thank you so much. Now over to Professor Kuldeep for formal vote of thanks.
Okay, thank you, ma'am. Good evening to everyone. At the end of second day of this ongoing 3-day evening's webinar on More is Different Legacy of a Nobel Laureate to celebrate the birth centenary of Sir P.W. Anderson, I take this opportunity to present a formal vote of thanks. We are privileged to have expert talks by our two speakers, eminent researchers and academicians, Professor T.V. Ramakrishnan and Professor G. Bhaskaran. I would like to thank Professor T. Ramakrishnan for his very insightful and enlightening, thought-provoking talk on Anderson's stance in physics, highlighting the work of Anderson in very nice manner and sharing about Anderson's approach uh, toward presenting the physics in a simple way and about Anderson localization model, electron nuclear double resonance, and telling us about Anderson model of spinless quantum electrons and how this localization theory further can be used to detect the tumor. It was very interesting to see, to have knowledge about this. Thank you, sir, for your very wonderful talk. We are very honored to have you, sir, today with us. Moving on further, I would like to thank Professor G. Bhaskaran, sir, for very interesting and enlightening talk on Anderson's work, highlighting Anderson's work and how kind he was. Thanks for sharing about your great association with Anderson, and telling us about how sharing with us how Anderson used to tell PhD students that be happy and have a lot of friends, and this is really a good thing for a real researcher, and how Anderson presence make difference in conference workshops when he share ideas in a very simple way with the audience. This was very interesting to know about his life, and thank you, sir, for telling also us about your Tower of Anderson model and theories, and also telling us about Anderson believed in importance of thinking in generalities, and uh, also sharing us with us how about Anderson saying that however realistic models maybe look like, solvable model have a great merit as they take physics to new domains. So this is very interesting uh, to see this, and also sharing with us uh, about Anderson Higgs particle discovery and his contribution in making BCS theory and Higgs phenomena acceptable to the people, uh, and his contribution was a lot in this. And also, thanks for sharing physics, saying by Anderson that physics has remained exciting and wholly absorbing as I age. So this is really very interesting. And moving on further, I would also like to thank to Professor P.C. Deshmukh ji for chairing today's session in a very nice manner and interactive manner. Thank you, sir, for being with us. We are honored to have all of you with us for a very nice session and very interesting interaction. I would also like to thank President IAPT, Professor P.K. Aluwalia, sir, Professor Arun Groban, sir, Professor S. Ramakrishnan, Professor K. Dharamveer, and our IAPT General Secretary, Ma'am, Professor Rekha Godpade, and all other dignitaries present with us on this occasion, and students, all IAPT members, teachers, and guests who are present with us in this session. And at the last, I hand over the stage to Dr. Sapna for final remarks on this session. Thank you all for being with us on this nice and great occasion.
Sorry. Thank you, Dr. Kuldeep. And with this, we come to the end of this second day, and we eagerly look forward to an exciting third day tomorrow, where we have one talk by Professor G. Bhaskaran, and the title of the talk is very interesting. There is a room for room temperature superconductivity. So we are eagerly waiting for the talk, sir. And after this, we'll have a panel discussion on opportunities